the amount of time on the target driver will keep IOs on the queue. And again, if that is non-zero consistently, your drive is probably saturated. The second way that you can have commands on the wait queue is that you can saturate the target, so the disk, and it will, on a SCSI transaction level, it will return what's called a queue full, and the driver will take that as, no more, I'm going to queue these. And it has to wait for the drive then to say, oh yeah, I can take some more. And that's going to be slower than the Solaris system, the target driver, managing the queue itself, because there's this extra communication. So we don't want to get into the situation of queue full. And the thing that can indicate that we are getting into the situation of queue full is this ACTV, active, which, if you see the same value in there consistently, or you're bobbing around, say you're bobbing around 8 consistently, and you've got high service times, that probably means you're hitting your queue depth. And again, if you consistently see command non-zero values in this wait column, that's the number of IOs that are sat on the wait column. Again, it probably means your disks are saturated. Okay. Was any of that unclear? What questions or concerns do you have? Okay. You can do that demonstration with paper plates, but I forgot. There was a W there. It's nothing to do with There was. I checked it. There was a W there, really. Okay. So dtrace, life-changing and wonderful. It has changed my life. And I haven't had to look at Solaris 8 or Solaris 9 for a long time. But how do they manage with truss and TNF probes? But this would be 60 to 70% of my dtrace use in those 5 patterns. And people say dtrace is hard. All right, but you can. There are patterns here, and so this top one here is basically saying, tell me what the most common system calls are, and then tell me who's executing mmap the most. And this one here is telling me whether we're reading or writing, who's doing it, and what the size of the reads and writes are. This one here is looking down at the target driver level, and it's asking the question of what size of I/O and whether they're read or write we're doing at the bottom of the operating system. So this here kind of looks at what the application is doing as we're going into the kernel. And this here is at the bottom saying, well, what are we sending out to the drives? Is the file system coalescing? Is it breaking things up? And the bottom one here, again, we're looking at the I/O, at the bottom of the target driver, and we're saying, what's the total number of bytes split up by path name? This is great. However, on ZFS, sometimes it doesn't work. Right? You'll just get, in effect, a blank field here. And the reason for that is ZFS will take blocks from disparate files as they're being written out. So if you have multiple processes writing, it will just stream them out, because that's an efficient way to write. So just need to be aware of that. Okay. Question? Sir?
When you're looking at I/O, you keep talking about disks. Of course, in most cases, it's not a disk, it's a SAN. It's like your HBA cards, your code switches, your write cache on your storage arrays. Where do you find things actually tend to go wrong?
Can you repeat the question?
So, disks aren't just disks. So I think there's an overloaded term here. Oh, right, let's go back. The question was, basically, how do you work out where, or where have you seen, or how do you work out where on the wider storage fabric the problem is. So I use the term disk to mean anything that looks like a logical disk. Okay, so not just the spinning rust in a frame. So there's a couple of answers here. Is that one, to an extent, if somebody else or some other vendors provided the storage, then it's sort of blame management. I know it sounds kind of, but it's to say, well, here's my evidence from dtrace, from IOStat. This is the behaviour. I'm telling you because it's helpful, but it's not our fault. So there are common things that come into play. One is front-end processors run out of steam. That's one of the most common that I've encountered. Another is caches on large data frames will start flushing themselves. Another is that the pattern of I/O, the intelligent caching, either read or write, just can't cope with that pattern. Another favourite is that PCs are plugged into mission-critical servers, and the HBAs go faulty, and you've got absolutely no visibility from the Solaris host that the front-end ports for the storage are spending all their time answering this request that makes no sense at all. So they're not dealing with, the SEC requirement for reporting. They're they're trying to answer this gibberish that's coming from a failing PC HBA. But sometimes it is, most of the time from my point of view, it is just saying, well, I actually don't, I don't know your storage. I don't know how to troubleshoot it. But here's the evidence I can give you from IOStat and dtrace, whatever other tools. But often we're not in a position. And I think this is maybe one of the performance analysis. What you're trying to do is get blame. Firstly, is get blame in the right place. Is it the application? So at the start, do we run VMstat and MPstat and PRstat? Look at where the time is being spent. Is it in the kernel? Is it something we should need to be tuning, fixing as a bug? Or is it external? Is it network saturation, maybe network latency issues, retries? Or is it a disk retries latency? Or have we got some other sort of resource, memory or CPU? And the first step is to find out which of those user land, kernel, resource on the box or resource external. And that's the first place to break it up. Does that answer your question? Sort of. We can come back to that if you want. Right. So another theme, and this is that's kind of quite pervasive and often low-hanging, very low-hanging fruit, is let's say the Solaris memory allocator, like all memory allocators, is imperfect. So the default memory allocator for Solaris is a single-threaded libc-based allocator that does malloc and free. If two threads in the same process want to do malloc and free at the same time, they will have to fight it out for one uber lock. One will get it, the other one will have to wait. There is, if you were to find a perfect user land allocator, it would have these attributes. So it'd be space efficient, fast constant time allocation, per CPU caches, would not fragment, would return unused memory to the OS, have no thread lock contention, and we deal with legacy coding issues. And this is one of the reasons that we've stuck with the default allocator being the libc allocator. So there are applications out there that will do things like double freeze, and libc can cope with that. Multi-threaded allocators can't necessarily cope. And we take sort of binary compatibility incredibly seriously. But the perfect allocator cannot exist. So we have a choice. You provide you with 6 here, and then there's other allocators. There's a GNU allocator, there's a Horde. So this is libc is kind of the one that's there by default. And the two I'll point you at would be mt-malloc, which you've heard of that sort of mt-safe, mt-hot. I think up until quite recently, kind of nt-tepid maybe might have been the best description. But there's been some really good improvements, as I think have gone into Solaris 10 for mt-malloc, and in some cases where it can outperform libum. But libum is very often the answer where you have malloc-based issues. It's used with it for things in Solaris like the SNF daemons. But I've yet to find a problem introducing it to an application which has a libc, has had malloc contention, and then we put it on libum. I've yet to see a functional problem. So these are single-threaded, and these are multi-threaded. There should be a W there. Star Office, eh? So, how do we know? Well, we can go and look. So the first place to look is for PR stat -n. And if you think about PR stat, it has -n, it has user, system for a process, process name off on this side, a couple of data trap columns, and then LCK. And that is user land locks. And if that has a high value, as in 60, 70, 80, 90%, then this is and you're concerned about the performance of that application, then that's a good candidate. Then the next step for that is to go and look at plockstat on that particular process. So plockstat is a tool built on top of dtrace that will show you the stack for that process of threads that are contending on locks. So it could be malloc, it could be something else. So that line will give you 30 seconds and it will print out the stack. You sometimes find on a busy process, plockstat will just exit. There is a -x something that's described in the dtrace manual. If you come across this, just mail me and I'll tell you what it is. I should have put it in here. But if plockstat exits immediately on a busy process, there is a -x. It can be found on Google quite option. I can't remember what the option is. It can be found quite easily. And then look for malloc as the primary element in the stack. You'll see a libc malloc contending on the malloc lock. You can also go and have a look with dtrace on the process ID, put in there, and that executable, what the range of sizes of allocations. And it may be that for an application, it's an in-house application. One of the early T2000s to come into the UK, I used a similar line to that to find out that a highly multi-threaded process was writing to a log file in 1 byte chunks. So all the threads were trying to write at the same time 1 byte to this log file. Now once they split that out, it went much better. But again, that's a very good dtrace pattern. And you can try this out with LD preload, a linker flag. And there's a number of knowledge documents, blogs floating around. But plockstat really sort of give you an idea. So a few other things here is that you can't avoid, every allocator has a different scenario for worst case memory fragmentation. For libum, if you're trying to do large allocations which are above 16K, then the allocator becomes single threaded. So I'll skip over that. But I think one of the things I'd like to get across is that memory fragmentation can happen. And ultimately, while allocators